Hello, welcome everyone to our NTech event for today. NTech, for those who don't know what it is a platform from knowledge to create a community around engineers through tech events. For the moment, because of the Corona situation, obviously it's only online events, but what we want to do is later to also meet in person. We talk about software, but also about life sciences, which of course in this time is very important for knowledge. So that includes also pharmaceuticals, quality assurance for pharmaceuticals and so on. So we do 1 or 2 events every month. Today presenting is Thomas. So he will give the presentation. During the presentation, you can type questions on the right side and all questions will be answered at the end of the session. Go ahead, Thomas.
Thank you. So I will start with the presentation. So in this presentation, we will go through the C++ evolution from how it evolved from C and through the most recent evolutions. We'll also take a quick glimpse into the future and what's being currently developed under the C++ standard. So we'll start with what is C++. C++ is a cross-platform compiled programming language, which aims to have a low-level access, low overhead, and give the developers full control over the resources and memory of the computer. Just as a note, this, of course, can be a double-edged sword, and with a high level of control comes a high responsibility, hence some of the principles to be used. C++ is used in many different applications. It ranges from embedded systems. As the embedded systems are becoming much more complex, the C++ can help compartmentalize the system in a better way. Also, game engines is quite a lot of them use C++. One example is Unreal Engine or Unity Engine. The C++ is their main programming language. The other example is operating systems. For example, in Linux, it's not in the kernel, as many know, but it's in user space. A lot of applications and a lot of libraries might use C++. And computer vision, often OpenCV, which is an open computer vision library, uses C++. And for example, OpenMP for parallelization is often used also with computer vision algorithms. Now, C++ can be integrated in many different programming languages. For example, in Python, you can see often used either C or C++ in order to achieve faster performance. For example, in NumPy, which is a library to work with matrices and big arrays. The underlying is written in C++. It's also very easy to wrap C++ libraries in C#. And from the other point of view, the C libraries can be used directly in C++ thanks to the way how it evolved. When the C++ was first born, but until even now, it stands on a few core principles. I will point out only a few of them. For example, the fact that the evolution should be driven by real problems is one of the important ones. There should be no big incompatibilities with C. And if in doubt, provide a means of manual control. That means that if it doesn't try to assume or force the programmers into a certain way of working, but it gives a very high level of control. Now, to get to the actual history, the C started as C with classes. It started in 1979 at Bell Labs, and originally it was meant to be an extension to C. And the topic at the time was to attempt to analyze the Unix kernel to be able to distribute it over multiple networks of computers and work together as a distributed system. Very fast, the need for actual programming language arose over this time. Now, there's just here's a list of the very early features, so you can see already from the early 80s, it was foreseen to have certain set of features like classes, derived classes, constructors, destructors, etc. And just a bit later, also inline functions, default arguments, and overloading of assignment operator were added. Now, the C was chosen to be kind of the part of C++, mainly to remove the need for completely starting the language from scratch, and also because at the time almost everyone was familiar with C++. There was a high level of support of C, and it reduced the need for support and documentation work in that case. Now, as the C classes evolved, it evolved to early C++. And this name, C++, was given to the C with classes eventually, and it was a play on words with the A++ or the plus operator in C. That it's a more than C in some ways. The main focus at this time, it was between the 79 and 89, was to improve the type checking and transitioning to a full compiler and not just extension of C compiler. And in 1989, there was a first official kind of a standard for it, which was the annotated C++ reference manual. It was not an official standard, but it can be considered as a first C++ standard definition. Now, we'll go through a few of examples of the early C++ to kind of get an idea of difference between the C and C++. One of the examples is an operator overloading. What it is basically changing or adding behavior to classes with standard operators like assignment, for example, but it could be a lot of operators. It's almost all of them, if not all. As a very simple example on the top here, you can see that it's the std string is a standard string operator, and you can use the plus equals operator to concatenate the strings. This is not done via the language itself, but it's through the operator overloading. So in theory, you can write the function directly, explicitly, with the str.operator plus equals. And you can see the same example in the std count, which is used almost in every C++ tutorial you might have ever seen. Another example is how you can actually define this operator yourself. It's again giving just a brief idea how to do one operator. And this is an example where you might have a point in a two-dimensional space, and you want to be able to do arithmetics on points. So you can define already a plus operator for points, where it takes the points and sums up the x and y element of the point, and then you would use it like any other, and it would result in a third point having 20 and 22 in the example. Now, another operator in C++ from very early on was const. It's a variable operator which marks to the compiler that this variable should not be changed after its initialization. It's used for immutable variables, and you can see a very simple example. If you defined the int const x equals 0, you can't ever change it again. The compiler will give you an error. And the other option is also you can use it as a function attribute, which tells the compiler that this function should not change any of the internal variables of the class. So again, as you can see in this line, you can see that it fails compilation if you try to modify the internal variable. Now, this is a useful, very useful concept because it allows to give variables and pass variables between functions and making sure that they will not modify when you pass them, for example, as reference. Which reference is the next concept? So we can immediately see that reference is something which in C you would achieve with pointers, but it's in this example, you can see if you define the variable x, it points to a memory which holds this value of 5. But you can define a reference which points to the same memory as the x value. So what happens is if I try to use ref, there will be a value 5. When I modify the ref, it will be value 20. But it also changes the original value x. Now, again, this is a very simple example just of the concept, but then you can use it, for example, to pass variables into a function and be able the function to modify the variables, as you can see in the first example, to swap 2 values. And you can also use it as a way to save unnecessary copies. So let's say we have a vector, and the vector is very big. Let's say it's a megabyte vector. And you want to pass it to sum its values and return the sum. If you would pass it without the const and reference, it would force the compiler to do a copy of the vector and copy on the variable. Here, if we define it with const and reference, it will allows us to save the need for copy, and because it's const, it will not try to modify the vector of the reference itself. So you can see it can also help prevent unnecessary copies in this case, and can help passing functions into big classes or variables. Another concept from early on of C++ is templates, which is again very different and not very C-like in this case. What it is, it allows for creation of parameterized classes and functions, especially in the early stages. Here you can see in the example what it does is you define the template and you give it a class, and what the compiler does, it kind of virtually replaces the class with the integer or float. This is a bit simplistic view on it, but it's the general idea that if we define the my_max int, the compiler will create a function with the int replaced with the types. And if you do it with float, it creates another function with the float instead of the type. This is good to keep in mind, that it will create a new function for each type you use it with. But it can be a powerful tool to improve on the code reusability, and you don't have to write 3 different functions with basically the same code thanks to this. We will not go much more into detail with templates in this talk, because we focus on big picture, so we will not go into detail here. But it allows for concepts like metaprogramming, but that will be again not covered in here. Now we are getting to the C++ 98, which really was released in the year 98 as a standard. So the C++ just as an overview at this stage was not owned, and it's not owned to this day by a company or a single person, but its evolution is driven by a community via a C++ standards committee. At the time of 2006, each member had to pay to be part of the community, and it was about $800 at the time. And every member has 1 vote. So if you are interested and people who are there and people who are interested, they pay and they try to influence the language in their way. And there's a very strong focus on backwards compatibility and avoiding change if it would have too big of an impact on existing code bases. Mainly, as you saw before, but in the example, C++ is used in many libraries and devices, and it would force the programs to maybe not update to the newer version if it would break their compatibility. Now we'll get to certain features. Again, the concept is the same. Some features of the C++ 98, which were introduced in the 98 ISO standard. One of them is std string, which has been used in C++ from 98, and it's used until today and keeps being extended. And it's basically operation on strings in a standardized and safer way than the C-style strings. And you can see you can define the string, you can get size, etc. This list is not comprehensive. There is much more things you can do, and that's being extended until today. Another example would be mutable. As we've talked about this const inside of the function, what mutable does, it allows and permits the modification of a class member even if the containing object is constant and should not be mutable. So you can see here in the function of area, you define the const, you define it as a const because you don't want it to modify the xy. But you can say, oh, I want to so-called cache the area here. And then you can actually modify the internal variable of the M area. What you can do still in the function is to modify n, x, y. So it's very specific to one specific variable or multiple specific variables. And it depends on the actual application, what you use it for. But this is very, very simple example just to understand how it behaves, not to showcase a specific function. Now, another very important concepts compared to C would be namespaces. In C, if you group, C groups all the names and all the global variables and the function names into one global namespace, and that results in a likelihood of clashes, or it results in these very long function names where you prefix it with all the prefixes there. And C++ 98 solved this problem via using namespaces, which allow separation of functions in their own logical spaces, and also classes and others. And here in the example, you can see that you can have completely the same function declaration in two different namespaces, but they can be doing very different things. For example, the point could be doing some of the point classes, which we talked about earlier, or the money could be making some of money. So they can have very different behavior, and that's why the namespace then can be referenced with this prefix. Now, this was the very brief examples from the 98 version, and in the 0.03, which was released in 2003, it was a very small version. It was a very small iteration. Main goal was basically to maintain and fix any possible issues or unclearances in the standard on top of the C++ 98. The other very practical reason at the time was that a lot of the main developers who worked on the 1998 version were a bit exhausted after 10 years of work, and it was another reason for just a more maintenance version. I will highlight two concepts. One is vector continuity, as now, oftentimes you use people are used to having the vector continuous, but it was not the case in the C++ 98, and they didn't have to be explicitly continuous at the time, and it did depend on the compiler. But since 03, it's enforced. This behavior is enforced. What it means is that the reference to the nth element of the vector should be on the same address space as the reference to the first advanced by the nth position in the array. The next concept is the value initialization. Basically, it's an ability to initialize the values inside of the struct or class with an empty initializer. This concept was again then much more extended in the C++11 and giving more possibilities. But what it helps with is that if you have a struct and you would define it on the stack like you would normally do, these variables would be semi-random. It would be basically what was on the stack previously. To save time, it would not allocate them. It would not define them to a certain value. But if you use the value initialization, it would define them and force their initialization to 0. So you would have a more deterministically behaving structures. Now, one of the concepts in C++ compared to a C would be the resource allocation is initialization concept, or RAII. It's a concept how to handle your data with classes in a clear way. Basically, thanks to classes and constructors and destructors, the resources can be bound to classes directly, allowing to have better control over their life cycle. It is to help also prevent resource leaks. Main two things it should do is that it should follow two simple rules in order to have it applicable to your code and your class. You should have to make sure that the acquiring of the resource is done in the constructor, or it throws an exception if the acquire of the resource cannot be done, if it would fail. And the second one, the destructor should release the resource and it should never throw an exception. I will show one example. Here's one example where you would use it for mutex resource allocation. Here in the first bad example, you see it uses the C style like locking, where you lock the resource, then you do your function where you need the resource for, and then you would release. Most of you probably immediately can see in this simple example that there's an error here, where if we do the early return, the mutex is never released, and hence we can result in deadlock situation. What the RAII concept does, it allows you to create, for example, this log guard where you acquire the mutex in the initialization, and as you do your function, you return. No matter where you return, or even if exception is thrown, the mutex will be released. And it's because of the concept of the constructor and destructor, where the destructor is called every time the object goes out of scope. Now, two, not extensive, but two things to watch out for from this examples we look through when you are porting C applications to C++. Mainly is to try to reduce the direct usage of C functions in all places in the code. So either if it's a standard function, use their C++ versions, or if you can't do that and you have legacy libraries, to contain the C function inside of C++ wrappers in specific places, and then use the C++ wrappers in the rest of the code base. And the other one is to try to not use this open close principle, and instead try to use the RAII principle where possible, or control the resources in their respective classes instead, because it's less likely to have a resource leak if you use these patterns correctly. Now we'll get to the second part of the presentation, which is focusing on the modern C++ evolution. And we'll start with the C++11. As you can see, there is quite a big gap between the C++03 and C++11. And this gap was not completely foreseen. You can see in some, the route to C++11 from C++03 was very long, much longer than it was expected. That's also why you can see, you can find somewhere references that the C++ OX, where it was still expected to come out before 2010. This might be also one of the reasons why C++11 extends the language and the library features one of the most from the at the time standards at this time. Again, I will go through a few examples to highlight some new concepts in C++11. Again, not extensive list because there's way too many concepts to go through all of them. Now, one concept is override. What the override does, it marks to the compiler the intent that we try to implement a virtual function from a parent class. You can see in this example, let's say we have a base class and we have a function to convert it to string. And then we want to derive from this class, but we want to override this this function to give the name of our new string. Here you can see there's a deliberate typo, mainly to see that if you say you override a function and you don't override an actual function from the base class, the compiler will give you an error. Before C++11, the compiler would be happy because he would assume that you are declaring a new function, and then you would have two functions, toString and toString with double G. And actually, when you would try to call the original one, it would call the base class one. Another concept, which is I find very useful in C++11, is auto, and often joined is decl type. What the auto does, it changed meaning before it was used for something else, but it changed meanings to be used as a type deduction. And what it does on the example, you can see, instead of using this std vector int iterator long initializer, you can use auto. And if you assign to the variable in the same line, it will be able to deduce the type of the variable. The similar concept is the decl type, where you can have a declaration of the variable based on a different variable. So let's say we want to have a temporary vector of the same type we are using in the code base. We can just use the decl type and give it the value. Now, why is it useful? It's first, it reduces the boilerplate code, like here, where the boilerplate code might not give us any useful information, and it just clutters the code and makes it harder to read. And second point is it also improves refactoring. So let's say here, if we would say, oh, now the vector is float in this function, you would have to change it in each instant where it's used. But if you use the code like this, you just change from int to float, and it will be just one place to change this. In the next example is the lambda expressions. So the lambda expressions, it's basically an unnamed function object, which is capable of capturing variables in its scope. This is quite known in other programming languages. For example, in JavaScript, this is used as a callbacks quite often. Inside of callbacks quite often. Here you can see in the first example, you can capture everything by value. So equals captures everything by value, and that it's accessible, which means by value means that it copies the values inside of the scope. You can also capture everything by reference, which is done with ampersand, and that just keeps the references to all the variables which are currently in scope. And you can also capture specific variables. You can also see that you can have specific arguments to call because it behaves like a normal function in that case. Now the lambda expressions can be very useful, especially if you are working with callbacks and you don't need to declare a whole function, but also it helps that you can give it the context you need, and then the function have the context it needs to operate without the callback function having to have this. In C, you would do it with void pointers, casting to a different variables, for example, which you don't have to do in the C++ thanks to this concept. And it can be also used for functional programming if any of you are familiar with the concept. Now, another concept would be range-based for loops. In C++ before 11, there was a if you wanted to iterate over a list or vector, you would have to do the iteration by index. In C++ 11, it's possible to use a so-called range-based for loop and iterate over the vector by values. Hence, you don't have to use the indexing. You can iterate over C-style arrays, initializer lists, or any type which has a begin and end function, like the vector one has it, or map, std map, or other std containers. The benefit of this is, first, it's faster to type and shorter, but mainly it prevents possible issues where if you are indexing by index value, there's more likely to have some out of bound access or errors in that type. Another concept in C++ 11, which is very useful and quite important, is unique pointers and shared pointers. Before the C++ 11, you had to always use the new and delete operators to allocate a dynamic memory. In C++ 11, you can use std unique pointer and std shared pointer. Now, the unique pointer is a pointer which makes sure that you have only one reference to this pointer. How it achieves it is that it doesn't allow you to do a copy assignment to a different pointer. The only way you can move it from one to another is using std move, and what it does, it moves the pointer reference to the ptr2, and it invalidates it in the ptr1. So if you try to use the ptr1 after the std move, it will not be possible. The second is the shared pointer, and the shared pointer allows for multiple references, and you can copy in between different pointers and share the ownership of them. But it uses reference counting in order to count how many references are being currently used, and when it runs back to the no references used, it will clear and delete the object automatically. Now, there is a bit of a caveat here. The shared pointer, you have to keep in mind not to make pointer 2 point to pointer 3 in this example, because that would create a cyclic dependency, and reference counting would not be able to clear it. So that's something you need to watch out for if you use shared pointers. So I would advise, if you want to use them, to read up a bit more into detail on the shared pointers. Here I'm trying to showcase what the concept can do. And that would be C++ 11. And we would get now to C++ 14. Again, there seemed to be a pattern in the C++ versions where there is a revision which is quite big, followed by a small one where it's doing more annotations and additions to the previous version. And the same was for C++ 14, which I will showcase a few examples. One is the make unique. So as we've seen before in the C++ 11, you still had this new parameter inside of the unique pointer usage, but you there was in C++ 14 the make unique function was added in order to remove the need to have this new function. What it's useful for, there are two big reasons. First, the new functions with the unique pointer was not exception safe. So it could cause, it still could have, if there would be exception during initialization, there would be some issues. Second, it allows to remove this duplication of the parameter. So here you have to define the class you are initializing twice, where here you could only do it once. And that's the main thing. The other from C++ 14 would be a deprecated, which marks the method that it's deprecated. And when the user then of your library, for example, tries to use that method, it will give him a warning in his compiler. And if he has warning that says errors, it could even stop the compilation. So this way you can enforce, you can tag the function as deprecated. Now we get to the C++ 17 as basically all the big features which were discussed during the C++ 14 development were forcefully pushed to C++ 17 to have again a big release with much more features in it. Now, one of the examples would be structured bindings. What you had in previous versions would be tuples, and the tuple kind of joins together multiple return variables, or not only return, but it joins together more variables. It would be similar to a dictionary in Python in a sense. And before C++ 17, you had to declare each variable before, and then you used the tie function to retrieve it from the above function. In C++ 17, it was reduced to be able to declare as an auto, and you then don't need to pre-declare all the functions before, simplifying the code. Now the tuples are useful in order to have a one return from function instead of return by reference, which you would have to have if you would have multiple return arguments. As an example of actual useful code would be you would have return error code and the actual value if the error code was successful. So you could use that as a tuple together. Now another quite useful feature to make the code more readable was selection statements. Selection statements, it's basically initialization statement inside of an if and switch code. If you would use it before C++ 17, you would use this first declaration, where you would have to first define the resource, then check if it was defined correctly, and then do your operations on it. Where in C++ 17, you can define it in the same if statement, and its lifecycle is contained by the brackets of that if statement. It's similar to, this one is similar to with concept in Python, if the one of you uses Python. The other one is you can use it also in switch, and it's basically the same concept, but in a switch form. And if, for example, if you have state machines, you can use it in that case, and you can unify the code and make it more cohesive. Another concept which I find very useful in C++17 are nested namespaces. And nested namespaces allow to condense this declaration of multiple namespaces in each other into one declaration. Now, this is useful, especially in more corporate setting. You would have multiple namespaces. Let's say you would have your company prefix. So if somebody else uses your library to have your own namespace, then you would have maybe your team, and then you would maybe have the module in the team as their own namespace. So it can explode quite quickly into how many namespaces you are having in your hierarchy. Other useful concept would be a string view. String view basically is the same as string, but for when you don't own the reference to the string you're trying to working with. For example, here you can have a reference to a string from different library, and you want to still perform some operations on it, like compare, find, or some other edit later. And this can help in unifying how you work with strings you own, and also strings where you might not own it, or you get them from a C style libraries. And another very useful concept is std file system, which is a standard library way of working with file system. If you worked on a code which has to run on Windows and Linux at the same time, you often get into the issues with how do I format the file path, how to create a directory, and then you have to have your own implementation for different ways and using different APIs. This aims to simplify this. And then you can have operations to check if a file exists, to have the file size, create directories, copy file names, etc., etc. As a note, this actually can still be used in C++ 14, but it's still experimental in that version. So it's to be used at your own risk, but it can be used in C++ 14 also. Now we get to the C++ 20, which is the most recent version, which came out just last year. And I will highlight a few concepts very quickly. One concept is coroutines. Coroutines are special functions which can have their execution suspended and resumed. You can see that how you define the coroutine by having the co-yield, co-await, or co-return defined inside of it. And in this example, you can see that it's co-yield used. And what it does, it suspends the execution before it's called again. So you can call it multiple times to get the value. Disclaimer, the generator here is not a standard function. That's something you have to implement yourself. And it works with promises, which is another concept which is part of C++ 17 already, if I remember correctly. Another possibility of example you can see is for tasks. And in this case, it would be having a TCP echo server, which would be a server which basically receives the data and sends it back. But it does so with the await, and the await suspends the execution until the function is resumed. And this can be used to simplify your networking code, where you have a lot of waiting and sending. Again, the task is not implemented here, and you need to implement it yourself in the C++ 20. I will touch a bit later on C++ 23 how this will be used in a bigger concept. Next, very quick to more simple example is that as we've seen that the init statement for if and switch was in C++ 17. In C++ 20, there was also this feature to add a range-based loops inside of the inside of the range-based loops. It's the same concept where you can define or initialize your values, and they only live inside of the brackets. And last example from the C++ 20 would be modules. Modules are this very relatively new, well, it's a very new concept to C++ itself, and it's a different way how to structure your code. Instead of using the header files and C files, it's a file with a IXX extension, and you can define what's external and what will be only accessible inside of that file. As some of you might know, in C++, there's often a problem, could be a problem with defining things in the header file and then defining the implementation in the C file, and this aims to improve it. For now, I've seen it only in Visual Studio Compiler, and it's not fully implemented in that compiler yet. Now I will give a few words about the future, which is basically the C++ 23. The C++ 23 is currently very much in the definition. It was planned to be face-to-face, but again, why we have these webinars and not in face-to-face ourselves, they are facing the same exact issues. And it's actually slowing down a bit their work from what I read from the mailing lists. A quick overview just about the features. As we mentioned, I will start on the modules and coroutines. We mentioned that the modules and coroutines were introduced in the C++ 20, but there's a plan to add a standard library support for them in the C++ 23. And one of the reasons for the coroutines support would be the networking. As we've seen in the task example earlier, it can hugely simplify the networking code, and it can take inspiration from the C++, from JavaScript, for example, how they use the event loop. And if you have an event loop based program, this can be also quite useful. And also stack traces to improve better debugging and crash tracing post-mortem in this case. Now, we are kind of at the end of the presentation. I will just touch on a few conclusions. The many new features are still being developed, and you can see in the last few years the C++ language has evolved quite significantly, and it's trying to be evolved more and more. So it's very much a live language, but because it seems to be much more faster advancing, I personally would still stick to C++ 17 right now and wait for the C++ 20 to be a bit mature, and maybe even the C++ 23 to have the full support of the coroutines and tasks before I would use it. But that's my personal opinion. And the C++, since it's evolving fast, there's this living document with the link, which I will share later after the presentation, with the email which comes afterwards. This document basically has a list of good practices and kind of core guidelines for C++, which are good to follow, and it can help your code to be more readable by others. And the more of C++ developers using the same guidelines, the easier it will be for us to read each other's code, because there's, as we mentioned in the beginning, C++ doesn't try to stop people using the way they want to work. And here's some small list of resources which you can, which I will also share later in the email. But I very much recommend the Clean Code by Robert C. Martin. It's not in C++, it's in Java, but it's focusing on a generic concept how you should write your code and how you can improve your code to be more readable and understandable. And there are a few other resources. And I would like to specifically point out also Antonis Kalandra's modern CPP features. It's a GitHub page with a lot of examples and explanations to a lot of the concepts, and it's very nicely structured. So I very much advise anyone who's more interested into more to follow this link, which I'll also share after the presentation. So thank you for your attention. It was a tiny bit longer than expected, and I would like to give the floor to Henk for the Q&A session.
Thank you, Thomas. That was a lot of interesting stuff. So we still have a few minutes left for questions if anyone has questions. And in the meantime, maybe Thomas, you can also show which other events are still coming up after this one. So these are events which are still happening in the near future. So any questions from anyone? I can type the questions on the right side. And Quinton is asking, is it intentional that there is a new standard version every 3 years? And I think no, it is not at all. They try to create the versions as they become available, but that there was 2 times every 3 years. I think that this is a coincidence. So do you have any comments on that, Thomas?
I personally think it's not necessarily a coincidence, because it seems that even from 2011, it's following really every 3 years, and I think it's more of a plan to try to always release at least something to advance the language, because otherwise they would wait. For example, with the coroutines, and I can imagine that it would be better to wait. But this is more of my opinion from what I've read about it, but I didn't read explicit information about this. I can check later.
So any more questions? The PowerPoint presentation, this can be shared to the participants. We will do that together with the resources which Thomas mentioned. And I would also like to say one of the resources, the book Effective Modern C++ by Scott Meyer, is really something that you should read if you want to get more into these modern versions of C++.
Indeed, I have that one also in the slides.
Yes.
I just didn't want to slow down too much. We are already a bit behind time.
Okay, if there are no more questions, then I think we can round up here. One more question. We hope to see you all again next time for our session about DevOps, which should be very interesting and which is also in English. Thank you very much for attending, and hope to see you next time. Bye.
Thank you very much.